Chromatographic separations are fundamental tools of the chemist. There are many different types of chromatographic analysis: liquid-solid chromatography, gas-solid chromatography, gas-liquid chromatography, liquid-liquid chromatography, ion exchange chromatography, paper chromatography, gel filtration chromatography, and thin layer chromatography. Thin layer chromatography, or TLC as it is often called, is a commonly used technique first developed in the early 1950s. Today it is frequently used in the laboratory to identify the components of a mixture, to check the purity of a sample, or to determine the best experimental conditions for the separation of a mixture by column chromatography. In fact, the theoretical backgrounds for both thin layer chromatography and column chromatography are closely related. However, unlike column chromatography, in thin layer chromatography, the mobile liquid phase ascends by capillary action through the stationary absorbent phase. While in column chromatography, the mobile phase descends by gravity through the stationary phase packed in a column. In TLC, the solid stationary phase is coated on the support plate that is usually made of glass or plastic. Commercially available plates, already pre-coated with a thin layer of the stationary phase, are generally made of plastic. In most cases, glass is used if the thin layer plates are individually prepared in the laboratory. Frequently, these glass plates are microscope slides that measure 3 centimeters by 7.5 centimeters, but they can be much larger.
To prepare thin layer plates in the laboratory, 2 clean dry plates back to back are grasped by their edges and dipped into a well-mixed suspension of the stationary adsorbent phase in a volatile solvent. Then the 2 plates are held in the air to allow most of the solvent to evaporate. The plates are then separated and set aside to dry completely. Immediately before using, the plates are often heated to activate the adsorbent. In TLC, as in all other forms of chromatography, the choice of stationary phase is determined by the properties of the components in the sample to be separated. A polar adsorbent, such as alumina, is appropriate for the separation of nonpolar components. A less polar adsorbent, often silica gel, is appropriate for the separation of more polar components. The sample to be separated by TLC is prepared by dissolving it in a minimum amount of a volatile solvent. Care should be taken not to use too much solvent, or the solution of the sample will be so dilute that the separated components will not be seen. Always use proper ventilation when working with volatile solvents. After the sample is dissolved, a capillary tube that has been drawn into a very fine tip is dipped into the solution of the sample. Then the tip of the filled capillary tube is briefly touched to the TLC plate approximately 1 centimeter from the bottom edge. Care should be taken in spotting the plate to keep the spot as small as possible. It is better to place a second spot of the solution on top of the first one rather than allow the diameter of the spot to become too large. Care should also be taken to make sure that the first spot is completely dry before the second one is added. The diameter of the spot should not exceed 2 millimeters, or it will be difficult to resolve the components of the mixture because they will overlap. If commercially prepared plates are used, a reference line at this position can be lightly drawn in pencil at the side of the plate. However, this cannot be drawn on glass plates because the adsorbent will fall off. The plate is now ready to be placed in the developing chamber. In its simplest form, the developing chamber consists of a wide-mouthed screw-cap jar that has been lined with solvent-soaked filter paper and has a small amount of eluting solvent in the bottom. There are 2 factors that must be considered in choosing a solvent. These are the solubility of the components in the solvent and the relative strength of adsorption of the solvent and the sample components on the stationary phase. If the components are very soluble in a solvent, they will be eluted quickly and move along with the solvent front, and little or no separation will occur. If the solvent is more strongly adsorbed than any of the components, then the solvent will replace the components, and all of the components will move along with the solvent front. Again, no separation will occur. However, if the solvent is less strongly adsorbed than the components, then they will be separated according to their solubility in the solvent and the strength with which they are absorbed by the adsorbent. The choice of eluting solvent is, to a large extent, a matter of trial and error. Generally, the best solvent is determined by running several chromatograms in a series of solvents of gradually increasing polarity until a good degree of separation of the components is observed. A mixture of solvents is often required to separate a sample into its components. The depth of the solvent should be less than 1 centimeter. Then the plate on which the sample has been applied is carefully placed in the chamber, making sure that the liquid level is below the spot and that the coated portion of the plate does not touch the solvent-soaked liner. The developing chamber is then closed and the separation of the components allowed to take place. Do not leave the developing chromatogram unattended, since the plate must be removed from the chamber before the solvent front has reached the top of the adsorbent. The plate should be removed when the solvent front has risen to within 5 to 6 millimeters from the top of the adsorbent coating. After removing the plate from the chamber, the final location of the solvent front is marked with a pencil. The solvent is then allowed to evaporate from the plate. The separated spots of the components of the sample mixture must be located. If the components are colored, they can readily be seen and their positions can easily be determined. However, more often the components are colorless. Therefore, other means must be used to locate them. This can be done by several methods. If the spots fluoresce, they can be irradiated with ultraviolet light in order to make them visible. The components then appear as bright spots because of the emission of light. Another method of visualization is to place the sample plate in a closed chamber that contains some iodine crystals so that the components can complex with iodine vapor. The components appear as dark spots, which should be outlined in pencil before the iodine complex decomposes. A third method is to impregnate the solid support or the adsorbent with a fluorescent substance before the separation process begins. Then the plate can be irradiated after sample separation. The background glows because of the fluorescent material that it contains, and the components appear as dark spots on a bright plate. It is also possible in particular cases to react the components with another reagent which will form colored compounds, thereby making the spots visible. For example, a ninhydrin spray is routinely used to detect amino acids. Whatever method of visualization is used, the distance between the initial and final positions of the center of each spot is measured. In addition, the distance that the eluting solvent has traveled from the reference line or initial spot is also measured. The ratio of the distance traveled by the spot to the distance traveled by the eluting solvent is calculated. Under identical TLC conditions, this ratio, called the RF value, is a constant for a given component. Therefore, if the same solvent, the same adsorbent, and the same temperature have been used in two different TLC separations, different RF values for the spots in the two separations mean that different components must be present. Duplicating experimental conditions is often difficult. Very often, spots of an authentic sample of the compound suspected of being in the mixture are placed alongside the spot of the unknown before it is developed. Identical RF values in these cases are more reliable indicators of similar components than if the trials are run sequentially. Because of the small amount of sample and materials that are required for thin layer chromatography, this is one of the least expensive means of separating the components of a mixture. For this reason and the simplicity of the procedure, TLC is widely used in clinical, regulatory, industrial, biochemical, and chemical laboratories.
The drug analysis of a urine specimen, the pesticide analysis of a soil sample, and the protein analysis of a new strain of hybrid corn all represent typical uses of this technique.